homework 35, 362, page 362, section 6.2, 1 through 17, odd, 41, 43, 49, 51, 53, 57, 65, and 67. Okay, so, you guys were already saying, the volume of a sphere, not the area, and the surface area is different. We're talking about the volume of a sphere, and you guys, do you know it? There's a formula.
I don't remember.
We're gonna derive it today. It turns out to be 4/3 pi, imagine that, times r to some power. What power do you think it's to?
Cubed.
It's got to be, right? The only, this is just some constant, and the only length there, if you're doing this in centimeters or something, right? The volume should be centimeters cubed, and so if that's your only length in there, it's got to be cubed, and indeed it is. And we're gonna get to that today. But first, what's the area of this rectangle?
3 times 5.
3 times 5, which is. Wait, I'm hearing a bunch of things.
I said 15 square units.
Yeah, 15 square units. Yeah. We're not gonna worry about units right now. But yeah, it should be 15, right? Now, one way to think about an area is that it's a length. You take some length and you extrude that length through some other length, right? So an area is a length times a length.
Yeah.
And as we've talked about, right, if your shape is weird, now we have ways of dealing with that, right? When everything's just boxes, it's really easy. And in fact, that's how we formed all of this. Like, what's the area from here to here? Well, the way we did it is we said you break this, you chop this up into little blocks, right? And each one of those little blocks is base times height, right? And then you take a limit, and it gets infinitely fine and infinitely curvy, and so you get the approximation in the limit goes to the actual value, right? Okay, anyway, so an area is a length times a length, but a volume
is an area times a length.
that's another way of that's a way of thinking about it, right? Is that you take some area now. I'm going to take this 3 by 5 area and extrude that through some length. I'm going to ask about 1,000 times today. I'm going to say, what's the volume of something? And what I want to hear is area times length. What's the volume? Well, it's an area times a length, okay? And this just makes intuitive sense. So what's the volume of this box?
30.
Should be 30 because, and we could do this a couple different ways, right? We could take this area, the area of this face right here, which is 3 times 5, which is 15. And then we extrude that through 2 units, right? And that would be 2, which would be 30, like you said. We could also have done that by taking the bottom, which is 6. 2 times 3 is 6. So an area of 6, and extrude that through 5. And last time I checked, 6 times 5 was 30. So I don't think we need to go into that. Everybody good with that? Yeah. Okay. Another way of thinking about this, if we want the volume of something. Now this is easy because everything's just nice and linear, right? You're extruding, this is just some rectangle that you're pulling through, like another, a straight line. You're not like curving or anything like that. Like this would be different if you had a 5 by 3 thing and you extruded it like this, right? And now you have some kind of crazy shape. Life would be a little bit different in that scenario, right? But in general, what we could do is we could say that the volume of this thing, yes, it's the area times the length. Okay, so area. That's a L. So another thing we could do, thinking about calculus here, is we could take this thing and chop it up. Right? I could chop it up this way into little slices. And then I could take one of these slices like this. And let's just imagine that I had chopped this thing up into n slices. So here's x1 all the way up to xn. And then I have the xith one, right? And I chop this thing up, and what we get is some slice that looks like this. Ugh. Here's this slice. And I could say, okay, hold up. Now let's just look at this one slice. I'm going to pull him over here, like this. So first off, since this is just a this is easy because the whole time this thing is just a rectangle. And it doesn't matter how far I've gone in this direction. That rectangle, the area of that guy is still 15, right? So the surface area of this face is 15. He has not changed, no matter how far I pulled him this way or that way, right?
Yeah.
But the volume is what? How do we compute a volume? It's a what times a what?
Area.
It's an area, so the ith volume here would be the ith area, which happens to be constant. But now times some length. And what is this length from here to here? Well, not quite.
Wait,
remember it's
that'd be
X
x
n minus x.
Well,
xi
it's-
plus 1 minus x.
we call it delta x.
Yeah.
Right? Yeah. And yeah, we go, what we could do is say xn minus xi, xn minus xi, or I'm sorry, x1, right, the whole length, divided into n parts.
Yeah.
Where you've seen this before, b minus a over n. And that's how we, in the Riemann integral, we define delta x that way. That's why if you integrate from a to b, it's positive, but b to a is negative, because you just flip the sign, right? That's why that works that way. But anyway, this length here is delta x. So we're looking for some area times the length, and we get the ith area times that length right there. So we're talking about the ith volume here of this thing. We chopped it into n bits, or n slices. And then we're going to add, what we want to do to figure out this full volume is add up the volume. The volume is the area this way times the length. The length is delta x. And the area, nice in this case, it has not changed. It doesn't change. It's always just a constant 15. So we could say that the ith volume is 15 times delta x. Okay? Everybody with me so far?
Yes.
Okay, so what I want to do then is add up all of those guys. I could say then the volume that we're looking for is approximately equal to, if I took the sum as, let's use I, goes from 1 up to n, of each one of these volumes, VI. Do you buy that?
Yeah.
I have n of them. That's all I'm doing. I'm adding up. Basically what this is this is volume 1 plus volume 2 all the way up to volume n, right? Because I've chopped this into n slices, and now I just add up the volumes of the slices. That's all I'm doing. But then what I'm going to do, because this is calculus, I'm going to say, to get the actual volume, I take the limit as n goes to infinity, understanding that when you do that, the dx, the delta x, which is xn minus x1 over n, that goes to 0. Okay, so n goes to infinity of this thing, I goes from 1 up to n, of the VI's. But that's the same thing as an integral. Right? And if we thought about this guy as being an x-axis right here, then he goes from 0 up to 2, yeah? And so we could say then, this is the integral of whatever the volume is, the VI volumes, which we'll get to in a second, from 0 to 2. But we're hoping that all of it, and this is the thing, I'm setting up something, it had better have this in it, right?
Yeah.
Right? Like, because if you're adding up infinitely many things, this part had better go to 0, and so indeed it's there, right? And so it turns out to be just the integral from 0 up to 2 of 15. because that's the AI. The delta x takes care of itself, and in the limit becomes dx. So what's this? 15 comes out, it's just dx. What's the antiderivative of dx? Or you could just think about this as the constant function.
It's just
15
Yeah.
integrated out to 2, right? But anyway, so that's 15 times the antiderivative of dx is x. Evaluate that up at 2 and 0. You plug into 2, you put it at 15 times 2, which is 30, which is what we expected. Now check this out though. This integral here, it's not exactly the same. There's no length that's 15 long here, right? Like
Yeah.
this integral, this function right here is not this area under this function is not exactly the same thing as our setup, but we're able to reinterpret this integral instead of saying, what this means is the area under this curve. We could say, well, hold up. We did a bunch of stuff here, and we got this integral, but that integral now represents the volume of this thing.
Not
that-
the actual thing, yeah.
Yeah, it's not that 15, it's not that this is this function. It's that we were able to say, well, you know what? I need to add up infinitely many volumes of something. And if that has the property that the length here, as we're adding this up, goes to 0, it's a delta x in a sense, then you could make an integral out of this problem. Yeah, cool. Now this is a trivial example because you gave me the answer before we even started all this, right? You said it's 30 because it's 2 times 3 times 5. And that works just fine when everybody's at right angles to each other and everybody's straight lines. That's not going to work so well if you have something like this. Here's number 52, I think. Was it 52? Yep, here's number 52. They tell you to find the volume of this object, and they give you a nice little drawing. It's a square. This is a square, and it has lengths a. So that's a times a right there.
Okay.
But also, hold up. I gotta get in front of it to do this right.
It's like a pyramid kind of.
It's like a pyramid thing,
So with the
yeah.
top column.
There's that thing. And I could do like this. Right.
Isn't there a formula for a pyramid?
There probably is, but let's derive it.
Yeah.
Right? That's the idea. There is. There is a formula, and we're about to figure out what it is. But this is a pyramid, and this is the... So, this length is a square. Here's A, and so it's A, and A. This down here is B. Each side is B, and B, and B, and B.
What about the other one? Do we not get that one?
Yeah. You need to know that it's an H. There's your height right there. Because that would change things, right? Okay, yes, yeah. And so we need to know that. Now, here's the thing. Now, find the volume. That's what it says to do. There's a bunch of ways we could go about doing this. And it's going to involve chopping it up and finding the volume, or finding the ith volume. I want to do this well here. Give me a second. Sorry about this. Let's do the bottom one first. There we go. Okay. Now one way we could do this looks terrible, is we could chop this guy up this way. And say, okay, same kind of thing here. I'm going to imagine an x-axis, and so x goes from 0 up to b, and then I chop this guy up. But let's think about what the cross-sections would be. If we did that, notice that now I'm gonna put them flat he's oriented back this way. I'm going to bring him so he's exactly flat this way. Okay, so we're going from 0 up to B. Up here, that length is A. Now you want to try to come up with a formula. The ith cross section of this guy, right there. Well, that's all well and good when you're from here to here. But what about when you're over here? What about when you're over here? You want to try to come up, because the idea is you want the ith volume. You know that's the ith area times delta x, because you've chopped this up, and every time this guy's going to be delta x right here. Why did you do it that way? Because you're trying to get an integral, and so the only way to get an integral is if you have some delta x somewhere. So let's do it that way. But now the formula for AI is going to get weird. It's going to be really weird.
Break it up into 3 different.
You'd have to find out, okay, in terms of A and B, where is this? In terms of A and B, where is this? So you'd have the integral for this one, you'd have the integral for this one, you'd have the integral for this one. That's kind of annoying. But check out what happens. So this is, whenever you're given one of these, look at your object and think about all the different ways you could cut it up. And ask yourself, what kind of thing do I get when I cut it up? If I cut it up straight up and down, like we just said, you're going to have something weird over here. That's going to be some kind of rectangle, and it's going to change a lot. We could do it that way. But what happens if I chop it up this way? If I chopped it up
We'll just have a bunch of
this way, are they rectangles?
or squares, yeah.
They're squares. And square, just the formula for a square is much easier to deal with, right? I mean, what's the area of a square? Well, all you need to know is one side. And so if you've chopped it up this way, all of those are squares. So I'm thinking that's probably a better way of going about doing it. Now, here's what I'm going to suggest is we could put an axis going straight up and call this my y-axis, or we could lay this thing on its side.
Yeah.
And when I do that, knowing already I know that there's symmetry about all of this, now I don't need to worry about laying it on its side. I'm going to do it exactly flat so that this thing looks like this. Because like I just said, I know that every cross section I've taken is exactly a square. All I need to know is the one length of this square this way. So I'm going to lay him on his side here. And now I could choose to put my axis here. That seems like a lot of work. Or I could choose to put my axis right here. And use symmetry again to say, well, hold up. If I just know this height right here, I should be good to go. Right? And so this is what I'm going to do.
Which is just 1/2.
Yeah, exactly. So here we go. This is how I'm going to set this up. We know that this total length is B. So if that total length is B and that's 0, this must be B over 2 right here. Right? Right? And down to negative B over 2 down here. Everybody got that? I'm going to need you guys to be a bit more quiet. And if you're going to play like that, please go into one of your rooms. Okay? Now let's think about this height here. If the total is A, again we go up to A over 2 right here. And down to negative A over 2 there. Okay, now what I want to do. Oh, and this right here, like we just said, is H. Right there. Right. So I know I'm integrating from 0 up to H. Now, I'm going to chop up my domain. Okay? Chop it up into little bits. Each one of them is delta x long. And now I want to find the ith slice. The ith slice right here. Remembering now that what I've just done here, that total length right there is the same here and here and here and here. Okay? So then my area, so I'm looking, right, I want the ith area. If I could find this height right here, I'll just say then the total length is 2 times that height. See what I'm doing here? I'm making my life easier by just forgetting this down here.
And then just multiply it.
I'm just going to multiply it by 2. So whatever this height is, let's call this height y. Whatever that is. At the ith one, we're going to get some yi. And then the total area of, that's the area of this thing, right?
Yeah.
That area should be, well, let's think about it. Y is half of it, so it should be 2y, right?
Yes.
And then I take that and square it, right? Because it's just, that's the total length. Square it, because it's a square, I'm using it to my advantage, that should do it. So here we go. And delta x is the width, right? Delta x right there. So the volume should be 2yi squared. That should be the ith volume. Now, here's the hard part. We need to find an expression for that. This is a line, yeah? So this is a function that goes from here to here. We should be able to, so in other words, y equals mx plus b.
And it's just rising.
And, uh-oh, there's a b here. Let's do capital B.
So the slope is just y. So
And we happen to know what b has to be.
yeah.
It has to be b over 2, so that's nice. So y equals mx plus b over 2. And the slope is what?
B over
B
2 over
over
a over 2.
over h.
Oh, no, over
So it's the distance here. So
oh wait, yeah.
yeah, so b over 2 minus a over 2.
Yeah.
Or how about b minus a all over 2 over h,
Yeah.
right? So there's the total, there's the run. The rise was that, the run is that. So my slope has to be b minus a over 2 over h. I could rewrite that as b minus a over 2h. That looks nice. So let's plug that in. Ugh. Here we get b minus a over 2h x plus b over 2. Now when I plug in an h, I should get out an a over 2, right? Plug in a 0, I get out a b over 2. And yes, I could see that. Plug in a 0, I get out a b over 2. When I plug in an h, I get b minus a 2h times h. The h's cancel. I get b minus a over 2. That's the same thing as b over 2 minus a over 2. Uh-oh. What did we do? I'm glad we checked this. Is that a positive slope or a negative slope? Ah, it's negative. Should have made that negative at the beginning. Making this negative.
Yeah.
Which we could write as a minus b. Everybody got that?
Yes.
Good thing we checked. Good thing we checked. Because I realized, as I started doing this, that I did it wrong here. I used a and b as half of it instead of a over 2.
Oh.
Yeah. I went, oh, it's a height of a. No, it's a height of a over 2. Yikes. Everybody following me here?
Yes.
Yeah. Okay, we have, now here's our function that we're integrating over. Remember, we've taken a volume, we've reinterpreted it now as an integral of something. This is the function that we're integrating now, right? Yeah. And so, the 2yi would be xi, yi, like that, right?
Yeah.
And we could double check, plug in. I want to move on, but you plug in your h, it'll work out to give you a over 2. Okay. So 2 times that, I can make life a lot simpler by doing that. I'll just vi is 2 times this function, a minus b over 2hx plus b over 2. We take it and square it, delta x.
Yeah.
Right? Now the 2's are going to cancel. The 2 distributes in to both of these. He's gone, he's gone, he's gone. And now we have a minus b x plus b
over
on a squared delta
Isn't
x.
A minus B over A?
H, thank you, over H. Okay, so that's my VIth area right there. And we want to sum up all the areas, and so this is the integrand, right? That's what we get. To get the volume, we take the limit of the sum of these, but the limit of the sum is the integral. From where to where?
0 to H.
From 0 up to H, from 0 up to H of this function, dx. And so you'll get your a minus b over h, x plus b. I would think the easiest way to do this is square it out.
Yeah.
Or you could do a u substitution, right? What?
That
Here's,
works.
huh?
Nothing. Yeah.
Yeah?
Yeah.
U substitution would be fine. Now, I'm not going to, with pretty much all of these today, I'm not going to actually solve any of them. You could plug this into Wolfram Alpha and do it yourself. I did that, and I was going to write it up here, but when I realized I did the wrong thing, that's not going to help you. So plug this into Wolfram Alpha and see what it is. And yeah, questions on this?
So it's just
You're going to be given some kind of volume to find. And the idea is, I know I'm going to cut this thing into slices and add up all the slices of the individual volumes. There's infinitely many ways you could cut this thing up. You could cut it up sideways so that your cross sections look like this. And good luck finding the area of one of those, right? So really, chop it up this way, and I would suggest with each of these, just think about what would it look like if you were to chop it up. Chop it up this way, okay, it looks like that. Chop it up this way, it looks like that. Oh, these are squares. Squares are simple. Maybe I'll try that way first. And then you try it, and yeah, I get to something. Okay?
Will you be doing with this like with curves, three-dimensional curves like that?
Oh yeah. Oh, yeah, that's what we're doing. This is, and I wanted to say, I wasn't even going to do this example because this is like, you might have one or two of these. We're going to be worried about this kind of stuff now. Yeah. The cool thing about this though is these are much easier. I think this is way more complicated than what we're about to do. Okay, so volume of a box or a rectangle. Okay, cool. Now we want to see what is the volume of a sphere. And if you type this into your favorite search engine, it tells you this. So let's derive that. Now, okay, so I have a sphere of radius r. I'm going to put it somewhere on my XYZ axis. Where do you want to put? You want to put it over here, here. Let's center the sphere, okay? So that he goes from negative r up to r. Okay? Now, the sphere, I haven't drawn him, but he comes out this way, right? In fact, we could think about this sphere as what's called a volume of revolution. Not like circa 1776 revolution, but if we took, say, a function, like let's just say this top branch of this function, and we rotated it about the x-axis. Now we could do this the other way too, but it'll be easier if we do it this way. And if you rotate this function around this way, what you end up getting is a sphere, right? It's a terrible drawing, but you get the idea, right? You take your function and revolve it around an axis or a line. That's gonna be weird, but when you do, you have your function, you revolve it around an axis. Then, in every case, if you cut up that axis that you've revolved it around, then one of those cross sections is going to be what?
just another circle. Just a smaller circle.
It's a circle. Even if it looks like this, right?
Yeah.
When you revolve this guy around, you're just revolving it around And every one of these cross sections is then a circle, right?
Yeah.
Do we know what the area of a circle is?
Pi r squared.
Ah! So, okay, we want to find the volume of a sphere of radius capital R. And what we're going to do is chop up the x domain. So first off, what's this? We're just going to think about it as the top function. What is the formula for that top function? Y.
X squared
Squared
minus
plus y squared.
no of
Wait,
r
sorry, yeah.
minus r squared minus x squared.
Let's check. Okay, that's that guy.
Yeah.
And if we solve for y, we would have r squared minus x squared. We take the square root, and we can take either branch. I'd rather take the positive branch, and that's the thing that we're going to revolve around, like that. And so we have capital R squared minus x squared, like that. Okay, now, so I've chopped this thing into n bits, okay? And I want to take one slice of it. It has a width of what? What is...
Just delta x.
Yeah, delta x right there, okay? So here, I'm going to draw this a little bit differently here. That guy right there that I've taken, right here, looks like this. Here's your x-axis. And now, this thing is a circle. And what is that circle's area? Because that's the ith little bit that I've taken. What is the area of that circle? Well, we're here at, let's call it, and I'm going to stop with the I stuff for the x's because it just gets ugly. That's because we know what we're setting up, right? We're setting up a v1 plus v2 plus all of that up to vn, and that's the sum of the vi's, and we know we're going to take the limit of the sum, which is going to give us something, some function involving x. So I'm going to drop the I because it's annoying, okay? Right?
Yeah.
Right? Like as long as the function that, like, you understand what we're doing. And, okay, so the ith volume then, okay. What's a volume? It's a what times a what?
Area times area.
Okay, so the ith volume is the ith area times what?
Delta x.
Delta x, by design. That's right, right? Like the way I've done this is that every time, each one of those slices has a width of delta x. Now I just need that area. And the area of a circle is what again?
Pi r squared.
Capital R?
No.
No! And that's why I used a capital R here.
Yeah.
Is that this height now is my new radius. And I'm going to use lowercase r here. So pi little r squared.
Yeah.
So pi little r squared delta x. But now we need to get r in terms of x. So if I'm at x, r is just the height of the function, right?
So yeah, so just plug it in.
Yeah. And so let's just see. I'm going to take whatever r is. I'm going to square it. I'm going to multiply by delta x. So what is the height right here?
Would be big R squared minus little r squared.
Yeah, well here, I'm going to be really explicit. This is what we're doing, right? That's the height of the function, right there. When I plug in an x, I get out as my height that. That is the radius right there. Right? Same height right here. Yeah? And so that's that. And so my ith volume is then pi times, this is nice, r squared minus x squared delta x. Now, hold up. I want to be smart about this. Let's not integrate this entire thing. Let's just integrate this half. Yeah?
Yeah.
So I want to go from here to here, and then I'll say that the total volume is 2 times that.
Yeah.
Okay.
Right? So the volume that I'm looking at, the volume of a sphere, is 2 times this amount, which would be what? When I take a limit, this becomes what?
Integral from
The integral from where to where?
0 to r.
To which R?
Big R.
Big R of
That.
this stuff. See why I don't bother with the i's? Who cares, right? So here's this. R squared minus x squared delta. Oh, then in the limit it becomes dx. So that's 2 pi integral from 0 up to r of r squared minus x squared dx. That's 2 pi times, okay, antiderivative of r squared with respect to x.
1/3. Wait,
No, it's
no,
just
it's
r
just
squared.
It's just r squared times,
x. Yeah.
okay, so r squared x.
Minus 1/3 x to the third.
Yeah. Be careful. Now, cool thing about doing the 0 is when I plug in the 0, there's an x in each term, so he's gone. So I'm just going to plug in an r. Okay, so we have 2 pi times r squared times r cubed, minus 1/3 r cubed. So I have
2/3.
r cubed minus 1/3 of that. So 3 over 3 minus 1 over 3 is 2 over 3 r cubed. Yeah? Which is 4 pi over 3 r cubed. And that's what the internet said. So it must be correct. So that's the idea. Now this is what we're going to be dealing with, is our volumes of revolution. Okay? And in every case, if you take some function and you rotate it around some line, it might be an axis, it might be another line somewhere, then it's going to work out that that cross-sectional area is always pi r squared. You just need to find out what r is, and that could be kind of a pain. Questions before we move on? Now, like I said, we will not be we're going to compute one more. The rest of them, I'm just going to show you how to set them up, because once you get to this point, you should know what to do, right? Like, so, we're not going to go through, except for this next example, we won't be computing them. I have the answers for you, so if you want to check and all that. Now, this is cool. There's an object. It's either called Gabriel's horn or Gabriel's trumpet. And it is the object you get when you take the function 1 over x. You start here at 1, so you plug in a 1, you get out a 1. You take that function and you revolve it around the x-axis. Like this. And yes, we were talking about the Archangel Gabriel, Saint Gabriel, the Archangel. And we want to know what's the volume of this trumpet. Now we know that the area, now let me ask you this. The area under the curve from 0 to infinity of this is what? Or I'm sorry, not from 0, yikes, 1.
Infinite.
It's infinite, right? It blows up. We've seen this before, right? Because that's the same thing as log x, evaluated at infinity and 1, which blows up, right? So the area under it is infinite. Is the volume infinite?
It seems like it.
You'd
It's
think
an
so. I
area
mean, how could
times
it
a
not
length.
be? How could it not be?
Because it's times the length, so it's area times the length, so it's
It's gotta be, if the area is infinite, then the volume needs to be infinite too, right?
Yeah.
Okay. So let's chop him up. We're gonna chop him up into bits, and we're gonna look at the ith bit that we've chopped up. And we get, what's the cross section here? What's the shape of the cross section?
A circle.
It's a circle. So let's look at that thing now. Have our circle. And what's its width here? It's a disc. Well, yes. The cross section itself is a circle. The object is a disc. what's the width of the disk? Delta x. Okay, so I want the volume of this thing. The volume is a what times a what? An area times a length, and what's the length? Delta x. Okay, so now let's find the area. This is what is the face of this thing? It's called a what?
A circle.
A circle. Okay, and so it has the form of what?
Are we doing top
If we
half
know
or-
that this is r, it doesn't matter.
So it's... Oh yeah, because...
Right? It's a circle. If it's better for you to do the bottom one, do the bottom one. But at any rate,
Yeah.
right? If that's r, if that height is r, then the area of that circle is what? Pi r squared. Okay. Now, what is r? If we're over here at x, r is what?
1 over...
Right.
Well, yeah.
Yeah, it's just f of x. And that's like, we could do this totally generally and just say it's just f of x. That's the height. But here, okay,
Oh, yeah.
the height of this is 1 over x. So we have pi 1 over x squared delta x, which I'm going to rewrite as pi times 1 over x squared delta x. And since I'm about to do an integral, I'm going to rewrite that again as pi x to the negative 2 delta x. Good? So then the total volume would be the integral from where to where? 1 to infinity of
Pi x.
this thing. So pi x to the negative 2 dx.
Wait, this won't be good because we have a 1.
Wait a second.
Wait,
Hold
but
on.
this one did...
I don't want to use my brain yet. I don't want to use my brain yet. I'm not ready to use my brain. Now I'm ready to use my brain. Now I'm ready to use my brain. What's the antiderivative of this?
3...
Negative.
Oh, no,
no,
just
negative
negative
x
x
to
to
the negative
negative
1.
Negative x to the negative 1, which I'm going to rewrite as negative 1 over x.
Yeah.
Now, I'm going up to infinity, so I'm going to take a limit as n goes to infinity, and then I'm going to put a 1 in here. So here we go. Okay, pi times negative 1 over n, right?
Minus
Minus negative 1 over 1.
1. Yeah.
Okay, so that's pi times negative 1 over n plus 1. Can I take a limit of that bad boy?
We need.
What do I get when I take the limit?
As it goes to infinity.
As
Yeah,
n
it's just
goes
pi,
to
pi.
infinity, we get pi
Times 1.
negative 1 over n plus 1. This just goes to pi times 1.
Yeah.
So pi.
Wait. What?
Has volume pi. Infinity does not behave the way you think it's going to behave. You're like, if the area is infinite, then the volume certainly has to be infinite. Nope. Nope. Isn't that crazy?
Yeah.
Yeah. Yes, that's crazy. Yeah, that's all I gotta say about that.
It's
What?
area times the length. So if you...
Yeah.
An area is
times the-
infinity, then it,
But
unless the length.
Infinity times some number equals pi.
you see, it's not this area times the length, though.
It's
Yeah.
You know,
it's a different-
it's weird.
Yeah.
It's really weird. Is that the volume, and think about it that way, right? The volume is proportional to, right? So the ith volume is pi r squared delta x, which is pi 1 over x squared delta x. In the limit, this thing is going to 0 fast enough that because remember, we're not like so anytime you're talking about something converging, right, you're adding up what this when you do this right here, you're adding up a sum of a bunch of volumes, right? V1 plus V2, and you hope that these go to 0 fast enough so that this converges to an actual real number. And since you're squaring this thing, the actual volume is, when you add up the volumes, that happens to, because now you have 1 over x squared, the volume is going to 0 fast enough so that it converges to a real number. But the area, if you were just adding up the areas here, it's not going fast enough. Craziness. Yeah. I wanted to do that. So that's Gabriel's horn, Gabriel's trumpet. You won't have any of those, but I just thought that was so cool. But it's an idea, right? Like, and this is what we're going to be dealing with, is like, if you give me any F, and you revolve it around the x-axis, right, then this thing that you get, this new shape, the volume of this thing, it's going to have circular cross sections. And each one of these volumes is some area times delta x. That area, since it's a circle, has the form pi r squared. And since that height is just the height of the function, it's just f, whatever f of x is, squared. And so, the volume from A to B of this object that you get would be the integral from A to B, pi times whatever the function is, squared dx. So there's your formula if you want to plug it in. I suggest you don't do it that way, because some of these will blow your brain and you could just think, oh, I'll plug in my f into here. Yeah, hold up, what if we rotated it around here? Now you've rotated it this way. Uh-oh, we have a different object. So you don't just plug in your f of x. You got to figure stuff out, okay? And I suggest that when you're first learning this, you draw it just like I've done. You draw the object itself, draw a representative cross-section of it, and derive a formula from that. Okay, here we go. Number 12. Find the volume of the solid obtained by rotating the region. The region defined about the line given. So in each one of these, from like 1 to 17, this is what it says. It's going to give you a region, and it's going to tell you to rotate that region around some line that they give you, and then find the volume. So they give you the region. Y, it's defined by y equals x squared, y equals 4, and it says rotate it about the line, y equals 4. So if you're given a region, what's the first thing you do?
Draw it.
You draw the region. So let's draw x squared. X squared does this. That. Y equals 4 is a line like this. 4, so now I see the region that they've given me, right? It's the enclosed region. And we're going to take this region here, and we're going to rotate it about this line, 4. So the thing that we should get, and I suggest that you just draw this thing out, right? It should look like this. We're rotating it about 4. And when we do that, it should look something like this. Yeah? And then a cross section of it would be a circle like this. Yeah?
Yeah.
And, okay. There we go. So
it's kind of like a sphere, but just like squished.
yeah, a spheroid,
Yeah.
a paraboloid. It's called a paraboloid.
Okay.
And so, okay, let's see if we could find. So again, the ith volume is what? How do you find a volume? It's
Pi
a
times So it's
Well, what did it? You're
Area times
getting ahead of me. It's a volume is a what times a
area
what? An area times a length, and in this case, that length, that depth,
delta X.
is delta x. Okay, so it's that. Okay, so let's draw this guy. Okay, so we know it's a circle because we revolved it around a line. So this thing has the form of what? The area
R
is
squared.
what?
Pi r squared.
Pi r squared. The only thing we need to do now is find r. And here's the thing, because you asked a second ago, you want to use the top one or the bottom one? Well, let's think about this thing here. If we tried to find the length from here to here, first off, we need to find what function this is.
It's just a negative plus 8 maybe.
Yeah, right. I mean, I guess negative and then plus 8. That seems like a pain when I know what this function is.
Yeah.
This is given. This is the function f of x equals x squared. So I could find, how do we find the distance from here to here?
That's
Bigger one minus the smaller one.
oh yeah.
Right.
Yeah.
You go.
4 minus.
So this length right here, which we're calling r, you could obtain it by going to the bigger thing and minusing off the smaller thing. So the bigger thing is 4 and the smaller thing is what?
X squared.
X squared.
Yeah.
There you go. There's your r. So we have pi r squared delta x. R is 4 minus x squared.
Okay.
And so my integral is going to be what? So think, I mean, we could be tricky and do the half, but let's just set it up here for the whole thing.
Oh, from negative 2.
From negative 2 up to 2. And so my integral for the volume is what?
From negative 2
Negative
up to
2
2
of
of 4 minus
pi
x.
times
Oh wait, no. Pi times 4 minus x squared. Squared dx. Yeah.
Squared dx. And you can figure that out.
Yeah.
That's easy.
Just,
It works out
just
to...
multiply it out probably.
Yeah, that's what I did. I multiplied it out. 512 pi over 15 is what it works out to. Okay? Okay. Alright, let's do another example. We got a bunch of these. Okay, oh man. Same thing. Find the volume obtained by rotating the given region about the given line. Alright, let's look at the region. X and root x. So root x looks like this. X looks like this. And we could see what region they're talking about. Obviously not the region out here that's in. They must be talking about this region right here.
Wait,
that makes that 1.
but they meet at 1, so and then
Yeah,
you're
because that one.
revolving it around x equals 2. So wouldn't it be also another small region?
Let me make sure I mess this up. I didn't mess this up. No, this is fun. No,
So there would be
this
another
is-
region where the x is bigger than the root x.
From
one
isn't
to
that
two.
1?
Hold up. Wait. Let me see. Let me make sure I didn't mess this up. It's very possible that I messed this up. I did not mess this up. Okay. This is the thing around x equals 2. Here's that. Rotate it about x equals 2. I think I did the wrong thing here.
So it's like this, right? Yeah. And then there's also that region. And
Yeah. Okay, yeah. I'm sorry. Yes. Thank you. That region, and here's rotating it about there. Yes, I'm sorry. Yes, you're right. Now let's think about this. We're taking this thing and we're rotating it this way. So the thing we should end up with should look something like this, right? And this is the thing, we're rotating it this way. Yeah? Hey guys, could you keep it down, please?
Baby's doing it.
Yeah, I know.
oh, the entire thing.
Yeah. Well, it's just this, but when you rotate it around, it gives you this right here.
Oh.
Right? So that's the volume. And so, but it's only this region here that's being rotated around.
Yeah, we're still adding up all the volume.
Yeah, so let's figure
Okay,
this
that's
out.
good.
Now here's the thing. Like I said, you got to think about how you want to cut up your object. There's your object. It's that thing that you're going to get when you rotate it around. But if I'm cutting it up, that's cutting up a Y. It seems like a real pain. Maybe I could reinterpret this. It would be nice if I could maybe flip this way. And get this so that maybe we're rotating along 2 this way. Yeah.
Okay, yeah.
And now I have my, I want to switch my X's and my Y's. So here's my X, here's my Y. I want my Y's down here and my X's up here. And we're going to rotate around the line X equals 2, still X, but now that's an output X. And what's that guy going to look like? Well, here's this line. That. Yeah. And then this thing now is going to come down like this. And here's this thing here. And that thing comes back up like that. And touches, they touch. That looks ugly. Everybody like that?
Yeah.
And then we're going to take this thing and rotate it around. Or rather, we take this thing and rotate it around like this. And what we get is this gets rotated up. This gets rotated up. Like that. And that's the thing that we're rotating around. So in order to do that, we need these to be functions. What's this function? The bottom one.
Oh, what is it? Oh, it's just a bigger thing than this.
Yeah, hold up. These are the 2 functions in terms of X and Y. So now we want Y as a function of X. So what do I need to do to each of these?
Just swap the inputs now.
Yeah, I'm keeping it, I want my Y's as inputs. Yeah. So let's solve for X here. What do I do to both sides?
So y squared.
Y squared equals X is one of them. And then the other one, it's still just Y equals X. Or X equals Y, right?
Yeah.
So here, that one is the X equals Y. This one is the X equals Y squared. And does that make sense? Like Y squared looks like a parabola and etc.
Yeah.
That one? Okay, so let me redraw this. Now we've reframed this problem. Now I would usually, what I like to do, or what I've done at least historically, is put this in terms of X because it's on that axis. I think we're old enough now that I could make my inputs Y.
Yeah.
Okay, so let's redo this here. I have Y equals X. It's gonna do that. Or I'm sorry. This is Y or X. X equals Y squared down there. Now I have this thing that does this. There's that. This is X equals Y. Right there. And now here's the thing. I'm taking a region. I'm going to rotate this thing around. So when I do that, I get this type of thing. I'm going to do that here and get this type of thing. Do that here and get this. And now we're imagining here. Is my drawing decent? Can you see what's going on here?
Yeah.
Right, I've taken this thing and rotated it up and around.
Yeah.
And now we can think about this. There's my inside part. Here's my outside part. Like that.
Yeah.
right? That's what's happened here. Or ugh, that looks terrible.
How did I draw this one?
Yeah, so let's do it this way. I'm gonna make it long that way. Long that way. There's my delta y. Okay. And so then the face of this thing is right here. Like that. And so then this object looks like this. He's a disk, but he's got a hole in the middle. Right?
So we don't.
So we.
Now, one thing we could do, and this is the, so, actually I'm going to redraw that here. It's a disk with a hole in the middle. It looks like that. Now there's two ways we could go about this. What I like doing, the way I like to do this, is to say, hold up now. That's the same thing, if I had just taken this thing and rotated him around, like this.
Yeah. And just minus.
And then, yeah, so if I find the ith volume of this guy, and then I just subtract off the ith volume of this guy,
Okay.
right?
Yeah.
So here's my ith volume, we get it that way. And so I have that solid, that's a big solid block of stuff. And here I have a big solid block of stuff. And I'm going to call this my volume big, and this is my volume small right here. And what I do is if I just take the ith one, and I go take my big one minus off my small one, that should do it, right? And so then, okay, the radius then, because, okay, the ith volume is the, how do you find a volume? It's a what times a what?
Area times length.
It's an area times a length. And we're chopping this up, and this is my what axis?
Y. So
It's
it's
my
not
y-axis, so I'm going to call this delta y. Right. Here's my delta y. Here's my delta y. Everybody following?
Yeah.
The volume of this piece is the area times delta y. And here I'm going to do this. Volume, the big volume, the ith one, the small volume, the ith one is what I'm working on here. And I know that I'm just going to take whatever that volume is, the full thing, and then just subtract out the volume of the middle stuff.
Yeah.
Okay, so now, let's think about this.
It's like
That cross section is a shape of a what?
a circle. So
So it's, what's the formula for it?
pi r squared.
Pi r squared. Now we just need to find r.
Or
And I think r is going to be easiest to find, again, this way. Because I don't have the name of this function. Because I did such a good drawing here, I could just look back and go, I need all of this. I know that this goes through here at 2. And I need that distance. I could find that distance, but I don't have that function. I do have this function. So I could say then that r, this is my r, it's equal to what?
wait.
Height is 2.
So just about 2 minus y squared.
The 2 minus y squared. So that's pi squared delta y, like that. R, we found out, was 2 minus y squared. So that's my big volume I. Okay, now let's work on my small volume I. Again, the ith volume. A volume is a what times a what?
Area times length.
An area times a length. And what's this length here?
Delta y.
Delta y. What shape is that thing?
Circles.
It's a circle, so it has the form what?
Pi r squared.
Pi r squared delta y. But r, let's see, we all find it that way. It's actually not hard to find. But we have this, we know that this line right there is given by x equals y. So how do I find from here to here? What's that distance?
2 minus x. Or 2 minus y.
2 minus y. So r is 2 minus y. So I'm just going to plug them in, and I get that the ith volume is something squared delta y. The thing is that distance right there, so he's 2 minus y. Now what I do, I'll just take the integral of this, minus off the integral of this. So I have the integral. From where to where? We didn't figure that out. It should be from where to where?
0 to
2. So from 0 to 2 of this stuff right here. Pi 2 minus y squared dy minus the integral, same domain, same place, so 0 to 2 pi 2 minus y squared dy. Now another way you could have done this, so this is the way I would say to do it, or this is the way I like to do it. Another way you could have done this is to say, well, hold it, let's look at this thing here. Okay, so the way that we would find that is to say, well, hold up, this is a circle, and so it has a big radius r, okay, whatever that is, the big radius, and then there's a smaller circle of radius little r, okay, and so then that area there, the ith area, will be
Oh, it's pi r.
pi big R squared minus pi little r squared.
Yeah.
Big R happened to be the big one, right? Which was pi, we just found was 2 minus y squared, minus pi, the little one was 2 minus y
It's kind of doing the same thing.
squared. And then you just take that, multiply him, so here's your ith volume would be what you get when you take this and multiply it by delta y.
It's kind of doing the same thing.
It's exactly the same thing. It's exactly, and so you can figure it out either way, so that your integral ends up being 0 up to 2 of pi 2 minus y squared minus pi 2 minus y squared, all of that dy, and it's exactly the same thing as this. Okay, so I like thinking about it big volume, and we're going to pull out a small volume. That's how I like to do it, and you can figure out what that is.
Yeah.
That's Wolfram Alpha. Oh man. Okay, so here's 19 through 30. I did not give you any of these, but yeah. Yeah. Anyway, okay. There we go. So, is this making sense?
Yeah.
What we're doing? So I've tutored this for well over a decade, and I have found that what works the best for everyone is, hold up, I'm trying to find the volume of something. If I break it up into bits, blah, 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 this right here, this little picture right here, like, if you could solve this, if you could just say, okay, if I could just find the ith area and multiply it by this, your life is so much easier, right? Looking at this thing as a big thing, like what we just did, that was terrible, right? Like, this is, just break it into smaller parts and say, can I find a cross-sectional area? I know I've rotated something so it circles, right? Big circle has this area. Small circle has this area. Multiply that by a length. Life is good. Okay. Okay. They give you this thing, and they ask you a bunch of questions about it. I'm not going to draw the whole thing. I'm going to draw part of the thing. This is y equals x squared. You got that? This is y equals root x. And then they have some other parts of this and whatever. They call this region, that's a capital R, region 3. And then they say, number 28 says, find the volume of the thing you get when you rotate region 3 about the line x equals 0. X equals 0 is this line. So the thing that you get looks like this. Oh, and by the way, let's go ahead and get a point here.
That's 1.
That's 1 this way. What is it this way?
Still.
Still 1. Okay. So we take this thing, and it looks like this, and we're going to rotate it around. And so as we do that, it's going to come like this, and do like that, and it's going to look something like this. Right? So it's some kind of bowl, and it has a big outer part and a smaller inner part, like this. Right? Now again, I'm thinking the easiest way of doing this would be to chop it up this way, because I'm not chopping it up this way. That looks terrible. I don't even know how you begin to do that. Yeah. So it's kind of obvious which way I want to chop it up. But again, then I'm looking at lengths here. How about we flip this guy around? Yeah. So instead of x and y, let's put my x upstairs. Put my x going up and my y going down. Now this thing is going to look, I'm just going to draw this picture, just draw it again, so that it does this, and then it does this, and now it's being rotated around this way. So that we get this, we get this, like that. Okay. Cool? Now, let's find our functions. This one, what's the formula for this guy?
No, you can't have this one.
He was, which one was he?
It's just
It's x squared minus.
y squared. X equals y squared.
Wait, for the area?
Whoa, just the functions. I want to know,
Oh, that one.
the top function should be what?
x
X equals
squared.
y squared.
Because that was the bottom
Y
one, so
squared.
now we flipped it. Which
Right.
Oh.
So x equals what?
y. Oh, x equals
Y.
square root of.
Yeah,
Plus
that's
y.
this guy. So the plus y, this is the one we're going to take on the top. The bottom one would be the minus one if you want. But knowing that I'm going to do a volume of revolution, I'm not going to bother with the full distance. I'm just going to take this thing and treat him as a circle. All I need to know is its radius this way, which I get with that function right there. What about this guy? Where did he
X
come from?
squared. Y squared.
Yeah, and ask yourself as you're setting these up, like, does this look right? We get x equals y squared from this one, and he's that one. Y squared goes up, root y goes that way. Yeah, we got the right thing. So I'm going to do it my way, and say let's find the big volume and minus out the small volume. So big volume is what we get when we take this function, x equals root y, and rotate him around like that. Small function is what we get when we take root y, I'm sorry, x equals y squared, and rotate him around like this. Yeah?
Yeah.
Okay, so let's find the ith volume. I've chopped up my y-axis into little delta y's. Now I'm going to take this cross-section right here. So the ith volume is the what times the what? It's the what? A volume is a what times a
Area
what?
times length. So
An area times, and the length in this case
delta
is,
y.
okay. Now what's the area of this? Well, it's a, what object is it? It's a circle, so it has the form what?
Pi r squared.
Pi r squared delta y. R in this case is what?
Just square root.
Here to here. So let's just square root y.
Yeah.
And I take it and square it, root y, which is just pi y delta y. All right, now what about this guy? We take the ith y value, and we get our representative thing, and the ith volume is what times what?
An area times.
Area
delta
times,
y.
in this case, a length delta y. The area of this face is a what, and its formula is what?
It's a pi r squared.
Pi r squared delta y. And in this case, r is what?
Y squared.
Y squared. So pi r squared, but r squared is y squared. So I'm sorry, r is y squared. So we take that and square it, and we get that that one is pi y to the fourth delta y. So big volume minus small volume. I'm gonna say. So I'm integrating from where to where in y? From 0 up to
Oh, that's 2, right? No, 1. It's 1.
1. Careful.
Yeah.
From 0 up to 1. So, big volume is what? Integral from
0 up to 1
of
just pi times y dx y.
pi y dy, and I minus off the integral from where to where?
0 to 1 of pi times y to the fourth dy. Yeah.
Too easy. Hard, easy, right? Everybody got that? Okay, now, same region. I'll fix it later, buddy. I'm busy right now. You're gonna have to wait. Okay, same region. And we're gonna rotate R3 about x equals 1. Oh man.
Oh, so that. Because it's just.
So we're taking this thing.
X equals 1. I was thinking.
Yeah, y equals 1.
I was thinking y equals x.
Yeah. So now we do that. Oh, the last one. By the way. Oh, that's why. That's not what that is. So let's do this right. I looked at it, I was like, there's no way that you'd get that out of that. It's because this isn't squared, it's cubed.
For this one.
It was supposed to be the last time. And so then, instead of having x equals root y, it would have been x equals y to the 1/3.
Yeah. Okay.
And you do the exact same thing that we just did. And in the end, it would have been this thing squared, and so you would have had 2/3 antiderivatives. Yeah, okay. So, not too bad. But, so let's do it right this time. That's what this is. And we're rotating it about x equals 1.
Okay. Oh, this.
And it's still root x, yes, okay, okay. So now, let's just draw that region. We're
So it's
rotating them
basically the same thing,
around.
but upside down. Because we're not
this
going to
way.
rotate this one.
It goes
Right.
like this and like that. And now we're rotating it this way, so he goes here, he goes here, and that's the thing we want. Again, I don't want to chop them up this way. I don't know how to chop
It
them
should
up
be the
this way.
same thing, right?
What now?
It should be the same area as last one, right?
Maybe. We'll see. Let's just, hold up. Let's see. It looks like that, right?
Is it?
No, hold up.
Because the last one we rotated.
Yeah, but the last time big volume was given by this guy.
Yeah.
Now big volume's given by this guy.
Oh.
Yeah.
Oh, I see.
Yeah. And so don't try to outwit yourself here. Because you might just think, oh, it's the same. And then you just think, yeah, it's the same. But wait, is it? Hold up. Wait. Maybe. Now, I don't even want to think about it. So, that's one. Same thing we had here. Again, I don't know how to do it this way. So I'm going to reinterpret this guy this way.
Okay, yeah.
Now, rotating around, so this is my new y-axis, this is my new x. Rotating around x equals 1, so he's 1 there. And so this thing should go around this axis. He's going to come up and down. He's going to go up and down like that. Okay, now the outside one comes from this one. So he's that outside one right there, right?
Wait, no, wouldn't the outside
That
one be
outside one
X
is that
cubed?
one. Well, hold up.
Wait, okay.
X cubed is what's on the bottom, and that's what's being rotated about here. That's being rotated about here. And so this is my X cubed bit. He's the closest to the line around the axis of revolution.
Okay, yeah.
So he's got to be this one here.
Yeah.
And so when we get y equals 1/3 equals x, should be that guy right there.
Oh, yeah.
Or x, I'll do it as x equals y to the 1/3. He's got to be the innermost one. The outermost one came from root x. Oh, no, no. Yeah, came from root x, like that. That's this guy's root x. And so now he's the outermost one. So x equals y squared. And now I'm going to stop and say, do those functions look right? Does y squared go up like that?
Yeah.
And does cube root of y go like that?
Yeah.
Yeah, okay, okay, we got that right. Now we're rotating these guys around. I'm going to take big volume. It goes from one big guy like that. That's really dark. Representative washer looks like this. So the ith volume is the ith area times, we've chopped him up into delta y's, so it's delta y. And now the area is what? It's the area of a
Of the circle.
circle.
Pi
So it's
times r squared.
pi r squared. Now we just need to find what r is. I don't have a formula for this top function,
Yeah.
but I do have a formula for the bottom function, and so that's r.
So it's 1 minus
One,
y
there you
squared.
go. 1 minus y squared. So my ith volume is pi 1 minus y squared delta y. Too easy.
Squared, right?
Yes. Thank you. Yes. Okay. We're good. Okay. Small volume now is the one that we got this way. And he went like this and like that. And now we're rotating that guy around like this. We get a washer. The ith volume of that washer is an area times delta y. That area is pi r squared. R in this case, what's r?
1 minus the well, y to well, the cube root of y, or y to the 1/3.
Y to the 1/3. There we go. So that's equal to pi something squared delta y. See, that's how I always do it. When I do these, I do the squared first, parentheses squared, and then I plug my thing. I didn't do it that way, and I paid for it last time. Okay, so the volume, the actual volume that we're looking for of this original thing, is the integral from where to where?
0. From 0 up. Wait, that's just 1
No.
to 1.
To 1, yeah, because y is going from 0 to 1. 0 to 1. Okay, so 0 to 1 of the first bit, 1 minus y squared squared dy, minus the inner stuff, which is the integral from 0 to 1 pi 1 minus y squared dy. There we go. And is that what I got? Yeah, because I did it right this time. So that works out to 8 pi over 15 minus pi over 10, which works out to 13 pi over 30. Whoa.
It's all pies.
And it's all pies. Now, there's only one more thing we need to talk about before we need to go. There's this other kind of thing. Okay, everybody good with this?
Yeah.
Some people find this to be way, way, way harder than, say, partial fractions. I don't. it depends. Can you rotate stuff in your brain? If, you know, some people are gifted with, you know, being able to see things, being able to imagine objects and stuff. Those people usually do much better in this than, yeah. So it's really how your brain works. So, but some people, I say this every time, some people think this is the hardest thing that we're going to do in this class. And some people do, but yeah. So anyway, okay, last type of thing we're going to talk about. Here's number 44. It says interpret. Interpret as volume of a solid. And they give you this. And they suggestively wrote 1 squared as part of it. Now, here's the thing. You could interpret this as an area. You could say, well, hold up, this is just a function. This is just some f of x. Yeah? And this f of x is 1 plus cosine. Okay, so 1 plus cosine. We're going to take 1 plus cosine. So he looks like this. Then we're going to square him. So instead of having gone from 2 down to 0, I guess he goes up to 4 down to 0. So that's what that would be, right?
Yeah.
And then I guess we're going from 0 to pi over 2. There's pi over 2. Okay. And then we're going to subtract off 1. So the final thing we get would be I bring him down a little bit. He goes to 3. Comes down, maybe does this. Okay? So we could say, well, that's the area, this area. That's one way to interpret this integral. That integral, oh, and then times pi, whatever, who cares. But you see what I'm saying, right? Like, I guess I'll go ahead and do that. It would have been like a pi. So you shifted them down some more, whatever, who cares, okay? You could say, well, that's what this is. This is that area. But in the same way that we talked about before, like when we were talking about the volume of our cube, this 15 that we integrated from 0 to 2 is an area, but that 15 has nothing to do. This function, the constant function 15, that's not the function that we're integrating, right? Or rather, that's not the function that represents the volume. Same kind of thing here. We have some function that we're integrating, and that's the area, and da-da-da-da-da. Or we could say, you know what, there's another way of interpreting this as a volume. And I notice that we're integrating some stuff that's squared, and there's a pi in there. And so this is the same thing as this, minus, and I'm going to bring that pi over and break them up like this. Now, is this the same integral?
Yeah.
This is the exact same thing. Now we could see this, right, as like an ith volume. This is, right?
Yeah.
Like, this has that form,
Oh, yeah.
right? And so if that were the case, we could say, well, hold up, if that's a radius, we could think about that as the radius of some volume that's been rotated about I guess in this case, the x-axis.
Yeah.
Right? Because we're integrating with respect to x, we're going from 0 to pi over 2.
Yeah.
And so what's that radius? Well, that radius is this function right here.
Just 1 plus cosine.
Right? So in other words, the volume that we're integrating is pi 1 plus cosine x squared dx. And so this is like my pi r squared delta x. Just put a delta.
So r equals 1 plus cosine.
And so r, that's just where the function is 1 plus cosine, which looks like this. So if I took the function 1 plus cosine x, and I rotated it about, I'll do it a little bit better. If I took the function 1 plus cosine x, here's pi over 2. That's the function 1 plus cosine x. If I took it and rotated it around the x-axis like this, from here to here, then that's the volume I would end up with, right? And forget about these guys over here. Because all we care about right now is from 0 up to pi over 2. So that would be big volume there. Now we're going to subtract off small volume. And so small volume here, I guess, has the form pi r squared delta x. Well, I guess my r squared is, and you see they even wrote it like that to be suggestive, right? That's just the constant 1, the constant function 1. Okay. So in other words, if you took the constant function 1, and you rotated it about the x-axis, you would end up with a cylinder, right?
Yeah.
And the way that you would find the volume of that cylinder from 0 to pi over 2 is you would say, well, the vith one, it has that radius always. Its radius is always 1. And so the cross section of it would just be the area, which is pi r squared times delta x. And then you'd compute this integral right there. That's what it would work out to. And so we could see that as this volume then. Right? It would be what you got when you rotated this guy around, but then you subtract out the middle part. And so the solid that you're talking about is this thing. However you want to say that in your homework. I mean, something like this with a drawing would be nice, right? And then you say it's this part here. Like, you know. Does that make sense?
Yeah.
All right. So that's all I got.